I'm a geek coach, and today I will talk about Casimir effect. First, I want to talk about who Henry Casimir is. Henry Casimir was a Dutch physicist who made significant contributions to the field of quantum mechanics and quantum electrodynamics. He is best known for his work on the Casimir effect, which describes the attractive force between two uncharged plates in a vacuum due to quantum fluctuations of the electromagnetic field. However, he is also known for his research on two-fluid model of superconductors done in 1934. While at Phillips Net Lab in 1948, Casimir and Dirk Polder predicted the quantum mechanical attraction between conducting plates, known as the Casimir effect. This has important consequences in microelectromechanical systems, and he was also awarded 6 honorary doctor degrees by universities outside the Netherlands and received numerous awards and prizes. In quantum physics, a quantum fluctuation, also known as the vacuum fluctuation.
So this bottom part is fluctuating.
Yes, it's fluctuating.
It's a GIF
right. And it is a temporary random change in the amount of energy in a point in a space. There are minute random fluctuations in the values of the fields, which represent elementary particles such as electric and magnetic fields. Vacuum fluctuations appear as virtual particles, which are always created in particle and antiparticle pairs. Since they are created spontaneously without a source of energy, vacuum fluctuations and virtual particles are said to violate the conservation of energy.
Take it with a grain of salt. Some people say that, but it's not completely true. Continue.
Okay. This is theoretically allowable because the particles annihilate each other within a time limit determined by the uncertainty principle, so they are not directly observable, but their effects are detectable. The Casimir effect refers to the attractive force experienced between two uncharged parallel conducting plates or objects in a vacuum or a medium. According to quantum field theory, vacuum is not empty because it is filled with a background field at virtual particles, constantly fluctuating in and out of the existence. Those virtual particles briefly appear and disappear due to inherent uncertainty in quantum mechanics. When two conducting plates are placed close to each other, these virtual particles can be affected by the presence of these plates. The Casimir effect arises due to the restrictions on the possible modes of the virtual particles between the plates. Specifically, the fluctuating electromagnetic field can only have certain wavelengths or frequencies that can fit within the space between the plates, as you see in the figure. And this restriction leads to a difference in the energy density of the vacuum inside and outside of the plates, which is causing a pressure. And the net result is that there is a slightly higher energy density outside the plates compared to the space between them. This energy imbalance creates a pressure pushing the plates together. In other words, the Casimir effect generates an attractive force between the plates, causing them to draw toward each other. The magnitude of the Casimir force depends on several factors, including the distance between the plates and the geometry of the objects involved. The force is generally stronger for smaller distances and larger surface areas of the plates. The Casimir effect has been experimentally observed and verified to a high degree of accuracy, confirming the predictions of the quantum field theory. It has significant implications in various fields of physics, including nanotechnology and fundamental particle physics. Casimir, together with the Dirk Polder, also described a similar effect experienced by a neutral atom in the vicinity of macroscopic interference, which is called the Casimir-Polder force of a field. So Casimir force and Casimir-Polder force can also be formulated on the same footing. A thermodynamic analog is the critical Casimir force. It acts between the surfaces immersed in a binary liquid mixture close to its critical points and arises from the confinement of concentration fluctuations within the thin film of fluid separating the surfaces. Additionally, at Bilkent University, Giovanni Volpe and his team also studied nonlinear behavior of the critical Casimir force, as non-additivity, and this became the first experimental evidence throughout the world of non-additivity of the critical Casimir force. And these are my references, and thank you for listening to me.
Thank you.